I think my slides are visible, right?
Yes, sir.
Okay, fine. So in last 3-4 lectures, we learned the first law of thermodynamics and how it is applied to closed system, right? First applied to a process, then to a cycle, and how to analyze the closed cycles using the first law. Correct. It is time to move further and learn how to apply the first law for the open systems now. So what do we mean by open system? What is your understanding of open system? We talked about this open system. Hello.
For a system that can interact with the surroundings.
Okay. More specifically, we should think about this quantity, the mass, right? So in case of closed system, we talked about the systems having fixed mass, and we applied the first law for that entire mass. Correct. Now we'll introduce what is a flow device first. So I am going to take a simple flow device, and then we will differentiate between our closed system and the open system. Now for any system and for any process, we know how to apply the first law. So this is a general expression. Q is delta E plus W, which we have derived previously, correct? So this expression we are familiar with. This one, Q is delta E plus W. Now we know this delta E is nothing but the change in the total energy of your system, and out of this total energy E is made up of two components. This is the macroscopic form of energy, and this is the microscopic form of energy, right? So this is the kinetic energy, then the potential energy, and microscopic form is nothing but the internal energy of your system, right? So if I try to find out what is this delta E, if I put delta here, so same way you can put delta everywhere, and then rewrite this expression in this form. So Q is delta Ek plus delta Ep plus delta U plus W. So change in kinetic energy, change in potential energy, change in internal energy of your system, right? So we know this. Now we need to introduce the concept of control volume right now, and I'm going to ask you a question. What is system approach? You have studied this in engineering mechanics. I'm giving you hint. You have already studied this kind of approach in engineering mechanics, whereas this approach we are going to introduce now, control volume approach. This is also called as a CV approach, control volume. So whenever I write this capital CV, it indicates control volume. Hereafter, note on this. So what is system approach? Any idea?
So where we're isolating a particular object or something from the surrounding, and then we're studying it.
Okay. So if I talk about engineering mechanics, let us say you must have analyzed the situations like a ball is thrown in the air, right? And then you apply the equations of motion to that ball, right? Correct? We have done this kind of analysis in engineering mechanics. So this is nothing but the system approach. So in case of system approach, what we do is we apply the fundamental principles or fundamental laws to the entire mass or the fixed quantity, right? So if I say this is your ball, you are throwing this ball in the air, So whatever equations or the laws of motion you are applying, they are applied for this entire mass, right? And not like this is one particle of your ball or mass, right? So in case of system approach, we follow fixed identifiable mass throughout the motion, right? This word is important, fixed identifiable mass. So this is system approach. Now it is very easy to analyze this type of situation because you need not have to bother about each and individual particle present in this ball, right? So you are applying the whole expression to the entire ball itself. So system approach. Now sometimes you cannot directly apply the system approach as it is. So then we have to think about the second approach, which is control volume approach. So in case of control volume approach, now I will explain what is control volume approach using one example, simple example. Let us say you have a pipe like this, fine, and water is flowing through this pipe, right? Water is flowing. So this is the inlet and here is outlet, right? Now imagine, can you follow the fixed identifiable mass of the water through this device or through this pipe? Is it possible? It is not possible because continuously mass of the fluid or water is entering here and it is going out from this point, right? So it is very, very difficult to identify this fixed mass and follow that mass throughout its motion. Now how to analyze this kind of situation? So for this we are introducing this control volume approach. So in control volume approach, the idea is I'm least bothered of that fixed mass. What I will do is I will fix my boundary, and whatever enters that boundary and whatever goes out of the boundary, I'm going to analyze the effect of these interactions which are happening at the boundary. So I will treat this pipe as a black box, and I will only look at what are the interactions taking place at the boundaries, and I will account for all those interactions and see what is the net effect of this on the performance or what you can say the behavior of your job or behavior of your system, right? So let us assume this type of situation now. So we have a turbine like this, and this is the inlet from where some gas enters the turbine. It is expanded along this length of the turbine, and it will exit from this outlet. So this is your exhaust pipe, right? Inlet, outlet, correct? And this is the shaft of your turbine, rotating shaft. And then what I am going to do is I am going to fix the boundary like this. So this is my control volume actually. Whatever shown by the dotted line, this one is the control volume. So here I am not going to follow the fixed identifiable mass of the gas which is entering this turbine, right? So whatever may be entering, I am not bothered about it. So I will fix my boundary like this, and I will look for the interactions which are happening across the boundary. For example, if you look at this boundary, here some mass of the gas is entering through this inlet. So this is inlet for me, and I will look at what is the interaction happening at this boundary. Same way, if you look at the shaft, I'm getting some work output because turbine is a power producing device. So the work I'm extracting from the by work is extracted using the expansion of this gas, right? So this is the work of expansion. So I'm treating this as interaction at the boundary. Then you have this here. There is mass of the gas going out. So here is one more interaction. So similarly, there can be the heat interaction between the surrounding and your is happening at the boundary, and we will account for all those interactions, right? So what is the method of analysis for this kind of device? Now this is a flow device, so some fluid is entering here and it is leaving here, and in doing so it is doing some kind of work. Either it is producing some work if it is turbine, and if it is reverse, if it is compressor, let us say, then it will consume the work, because compressor is a power consuming device, right? So in that case this W direction will be inward rather than outward. So this is power producing device. So that's why this work is extracted from the system. So you can imagine these systems like the air compressor or the turbine or the pump, even centrifugal pump, or any flow device for that matter, where there is some fluid entering your system and going out of the system. So you can have the simple flow devices like heat exchanger, where you can have two concentric tubes, and the one fluid is entering through the inner tube and the other fluid is passing through the gap between the two tubes. So that kind of device can be also thought of as a simple flow device. So as long as there is some fluid entering the system and going out of the system, that system can be thought of as a flow device, right? Now the method of analysis for this kind of device is based on the two principles: energy balance principle and mass balance principle. So what we will do is, in analysis, we will write the energy balance, and we will also write the mass balance. And these two things are more than enough to analyze this type of situation or this type of device. Clear? Now can I go to next slide?
Yes.
So moving further, we'll talk about the steady flow process. Now what we mean by steady, first of all, we have to understand these single words, like what is steady flow process we already talked about. So what do we mean by steady flow process? The first point, so the rates of flow of mass and energy, these two are important words. The rates of flow of mass and energy across the control surface are constant. So whatever that boundary we have shown by dotted line in that previous slide. So if some mass is entering here, let us say mass entering per unit times m dot. Now the same quantity must go out m dot. So the rates of mass flow, and if suppose some energy is entering, maybe any energy you can randomly choose like this, same energy should be balanced when it is going out, right? So this kind of situation we will call it as the steady flow situation, right? So the rates of flow of mass and energy across the control surface are constant. So these are constant. Second, at the steady state of a system, any thermodynamic property will have a fixed value. At a particular location and will not alter with time. For example, if water is entering through this, and I am looking at this point, and let us say the temperature of the water is T degrees C. So this temperature will be T degrees C, right? And it will not change with respect to time. So if I see right now it is T degrees C, and even after 1 minute or 5 minutes, it will remain T degrees C only at this particular location. Then I will call this as a steady state of a system. Getting me or not? And it has definite value or fixed value. So let us say the water temperature is 30 degrees C. So it will be 30 degrees C. This fixed value is there, right? At a particular location, and it will not alter with time, will not change with time. Next, thermodynamic properties may vary along space coordinates. So now to explain this, let us say you have a steel rod like this or a bar, and you attach this to one plate like this, hot plate, and now this plate is heated. So what will happen? The heat will be conducted from this end to this end, right? And let us say it is open to atmosphere here. So what we observe is under the steady state, the temperature at any location on this bar will be constant. So if I take this point, the temperature may be, let us say, 100 degrees centigrade. So it may vary along length of this bar. So here it may be 90 degrees C, it may be 80 degrees C here, but at that particular location, it is constant with respect to time. So that is what the meaning of this. Thermodynamic properties may vary along space coordinates. So this is space coordinate, x direction. So along space, the thermodynamic properties may vary, but do not vary with time. So as the time changes, still the temperature will remain 90 degrees here. So you understood meaning of this? Steady. So in short, what we mean by steady state is, steady state means that the state is steady or invariant or does not vary with respect to time. So if I make a statement that let us say you have a friend, irrespective of whether you are a boy or a girl, if I say if you have a girlfriend who does not vary with respect to time, I will call her as a steady girlfriend. Same way, let us say we have the situation where this boyfriend does not vary with respect to time, we will call him as a steady boyfriend. So that type of analogy I am just explaining you what we mean by steady. So steady word is associated with time. So these two are linked together. So steady means something to do with time. Now, can I go to next slide?
Yes, sir.
Okay, fine. Look at this simple steady flow device. So this is just the general diagram we are taking, any random device. In last slide we talked about the turbine. So just random rectangle I am taking it as and calling it as a steady flow device. So what is the requirement for steady flow device is you should have at least one inlet and one outlet, right? You can have n number of inlets and n number of outlets. Right now this is simple device. We are taking one inlet, which is section 1.1, and section 2.2 is the outlet, right? Now the boundary of your this control volume is shown by this dotted line, right? So this is a control volume, right? And the surface which is separating your control volume or the volume within from the surroundings is nothing but the control surface. So this is control surface, this is control volume, right? And whatever the interactions which are taking place between the system and surroundings, all are noted down here. Now see the nomenclature. I think you should draw this diagram quickly and note down the nomenclature also. So what we will do is we will take any random datum like this. So I am taking one reference, right? So this can be any reference. For example, right now I am sitting in a classroom. So for me, this floor of the classroom is the datum, right? And my computer is maybe at a distance of 1 meter almost from the floor of this class. In this kind of situation, so computer is at a distance 1 meter from the datum. So any reference plane you are taking is a datum. Now look at the nomenclature. So capital A1 and A2, I am using this as the cross-sectional area of the stream at inlet and outlet. So if I say this is a pipe, then the cross-sectional area at the inlet A1 will be pi by 4 d1 square. So where d1 will be diameter of this pipe. If this is different section, like maybe the square I can have, or I can have triangular section. So remember, this is not always pi by 4 d square, it is cross-sectional area. It's cross-sectional area A1, A2. This will be measured in meter square. Then look at the next quantity, mass flow rate. So this term is called as a M stands for mass, and if I write dot, it means per unit time. So mass flowing per unit time is nothing but the mass flow rate, M dot. So whenever I use symbol M dot, it means mass flow rate, which will be measured in kg per second. Similarly, we have the quantities like P1 and P2 at section inlet and outlet. So P1, P2 is the absolute pressure, which is measured in Newton per meter square. Similarly, the next quantities are specific volume. This is specific volume, small v. V1 and V2 specific volume measured in meter cube per kg. Then the specific internal energy. Capital U is the total internal energy per unit mass, specific internal energy. So U1, U2 are the specific internal energy at inlet and exit measured in joule per kg. And C1 and C2 are the velocities, the flow velocities at inlet and outlet, which will be measured in meter per second. Now, if you refer few Indian author books, you will find they have used the symbol capital V here, V1 and V2 for velocity. I would suggest not to use these symbols. The reason being, we are using capital V for volume in case of thermodynamics. So for velocity, I am using intentionally. I am using the symbol C1 and C2 for inlet and exit velocity. Next, Z1 and Z2. These are the elevation above the arbitrarily chosen datum here. So Z1 is the height at which your inlet is located from the datum, and Z2 is the height at which outlet is located, right? And the last term, tau, or you can call this as a T also, huh? Doesn't make any difference whether you say tau or T. I may use this interchangeably. Sometimes I may say this is T also, that's fine. So this is time measured in, or tau, which is measured in seconds time. Now, what are these two quantities? This one and this. So you should note down. So d bar q by dt is nothing but the net rate of heat transfer through the control surface. So as I said, this is the interaction happening between the system and surrounding at this control surface. So this is the net rate of heat transfer through the control surface, which is measured in joule per second. Now we know Q is measured in joule or kilojoule, but its rate means its variation with respect to time. This will be measured in joule per second. So that's why this d bar q by dt will be given in joule per second. And we are not going to use here kilojoule per second. So it will be in joule per second, means watt, and not in kilowatt like this, kilojoule per second. So similarly, we have one more interaction here in terms of work. So this d bar wx by dt is nothing but the net rate of work transfer through the control surface, which is also measured in joule per second. Now this is important. This is exclusive of work done at section 1 and 2 in transferring the fluid through the control surface. So what is happening in this device is, when the mass is flowing through this inlet, it is forced through the control volume at this point, right? So you are forcing the fluid here, forcing in the fluid here, and here you are forcing it out of your system. So this is your control volume. So here you are forcing out maybe gas right now, if I assume, and here you are forcing in the fluid within your control volume. Correct? So these two works are not included in this. That is what the meaning is. Net rate of work transfer through the control surface in joule per second, exclusive of work done at section 1 and 2. So we have to separately treat those works happening at section 1 and 2. So we already talked about the flow work. So this is nothing but the flow work, which is happening at the inlet and exit. So flow work at the inlet section, flow work at the outlet section, right? So we have to account for those works separately. So they are not included in this. So what is this Wx by dWx by dt is made up of? I am going to talk about it more in the next slide. So can I go to next slide now?
Yes, sir.
Now remember, our analysis is based on two principles. One is the mass balance and second is the energy balance. So what we are going to do is we are going to write only these two the balance equations in the next slide. So and this is how we are going to derive the steady flow energy equation. So writing the mass balance first of all. So what we mean by mass balance is the mass rate of flow or mass flow rate entering your system or the control volume must be equal to the mass leaving the control volume. So if you have a random system like this, so the mass entering per unit time, which is nothing but the mass flow rate. So I would rather say the mass flow rate entering the system and the mass flow rate leaving the system m dot, these must be balanced, right? So I have only one inlet, that's why I have written m dot, and one outlet, so it is m dot. So these two must be balanced, right? So at inlet I may say m1 dot, at outlet I can say it as a m2 dot or m dot 2, right? So this is how mathematically I am writing this. M dot 1 is equal to m dot 2. Means mass flow rate at inlet and outlet are one and the same, or they are equal. So this is mass balance, correct? Now what will happen if this mass is not balanced? So let us say 10 kg per second is entering from this end and 5 kg per second is going out. So this is not balanced. So what will happen over the period of time? There will be accumulation of mass within this control volume. There will be accumulation of mass within the control volume. Then it cannot be called as a steady flow device in that case. Is it clear?
Yes, sir.
Yes,
So
sir.
mass flow rates must be balanced. Now somewhere you just note down how you write the mass flow rate or mass flowing per unit time. This equation is used in a lot of courses. Maybe in higher semesters you will use this equation again and again. So mass flow rate is given by the product of density, area and velocity. So if I say rho is the density, A is the area, and in next semester higher course you will use for velocity capital V you will use. So if I keep this notation intact, capital V, this is velocity, not volume. So mass flow rate m dot will be given as rho AV, mass flow rate. In our case it will be rho A C, because we are using capital C for the velocity, rho AC, correct? And now what is this density? I can write this equation 1. So m dot 1 can be represented by this expression and m dot 2 by this. See, this density is reciprocal of specific volume, or specific volume is reciprocal of density, or not? Get me or not? So this rho can be replaced by 1 by specific volume into this AC. So this is how I am writing this expression. Is it clear? So mass flow rate at inlet can be written as this A1 C1 divided by V1. This must be equal to A2 C2 divided by V2. The cross sectional area at inlet, velocity at the inlet, and specific volume at inlet. Same quantities at outlet. Name this as equation 1. So this equation is also called as a continuity equation. You are going to derive this equation again in the next semester in the course on fluid mechanics. So you will derive this equation using the elemental approach. But time being, you just remember this is also called as a continuity equation, or law of conservation of mass actually. Now next is we have to write down the energy balance for our control volume, energy balance. So before we write the energy balance, we need to talk about the work interaction happening between your system, this control volume and the surrounding. So let us talk about the work first, work transfer. So in case of work transfer, if you remember, we have taken this quantity d bar wx by dt, and there we mentioned that this does not include the flow work at inlet and outlet, right? So that's why I am splitting this work transfer in two streams. The external work, I will call this part as external work, and the other as the flow work. Now, what is included in external work is the shearing work. So example is also given. So in case of shearing work, you can have the work like the shaft work or the stirring or the electrical work. So any other kind of work can be included in the external work, right? So all those work terms, I will call them as an external work, and those are included in this. So you can have combination of different works, or simply the single work like shaft work or the stirring work, or maybe just the electrical work in case of if the current is flowing through a resistor, right? So those kind of works are attributed to this term d by wx by dt. And now the flow work. Now what is flow work? Just read the statement. So displacement work done by the fluid of mass dm1 at the inlet section 1 and that of the mass dm2 at exit section 2. So if you remember that flow device which was like this is your inlet and this is exit. So the idea is we imagine that there is some kind of piston here. If you remember, I explained this flow work. Do you remember or not? So you will imagine that there is some kind of a piston. This piston is pushing the fluid here within this section. It is pushing the fluid in this control volume, and here it is pushing out the fluid from the control volume. So this is the flow work at inlet, flow work at outlet. So these two we have to consider here in flow work apart from the external work. That's the idea. So the total work transfer we will calculate like this. So W is the total work transfer, which includes both this dWx by dt, which is external work, plus the flow work, right? So you should write it like this. So W is the total work transfer, which will be equal to Wx. Now this is Wx is this component, external work, minus P1 V1 dm1. Now what is this P1 V1 dm1? Why I'm writing this? Why I'm writing this term as a P1 V1 dm1? So if you remember, I explained you in the first 2-3 lectures on thermodynamics. The flow work per unit mass is given by this product of pressure and volume. So this is flow work per unit mass, right? Per unit mass. So if you multiply this by the mass dm1, then what you get is the flow work happening at the, or flow work taking place at the inlet. So you have to multiply by mass, because PV is only per unit mass basis, whereas this is total work done by the fluid mass dm1 at section 1 and dm2 at section 2. So the flow work at the inlet is given as P1 V1 dm1, and flow work at the outlet section is given as P2 V2 dm2. Now why we are introducing minus sign here is because this is the work done on the system at inlet. So you are pushing the fluid from outside in the your control volume, right? So this is negative work done on the system. So that's why minus sign. And here it is, your system is pushing out the fluid to the surroundings. So this is positive at the outlet. So name this as equation 2. If you have noted down equation 1 and 2, I will go to next slide. Can I go to next slide now? Hello?
Yes, sir.
Okay. So next task is to expand these terms now. So what I will do is, I want this kind of term, per unit time basis. So I have to differentiate this now. So equation 2, which was in the form of W, I have to differentiate this and write it in terms of the rate form now. So rate form is what? Differentiate this with respect to time. Find out per unit time basis variation. So I will write dw by dt or d tau, whatever it is, like this. Equation 2 is just differentiated. So you will get dw by dt is dwx by dt minus p1 v1 dm1 by dt plus p2 v2 dm2 by dt. Name this as equation 3. Now we know this dm1 by dt is nothing but the mass flow rate at the inlet. So this term will be replaced by m1 dot. Similarly, dm2 by dt is the mass flow rate at the outlet. So it is replaced by m dot 2. The rest two terms are kept as it is. And name this as equation 4. Next, say the total rate of flow of all energy streams entering the control volume must be equal to the total rate of flow of all energy streams leaving the control volume. So don't you see that this is the energy balance, right? So whatever the form by which the energy is entering the control volume, in the same rate the energy is going out of the control volume also. So these two rates are balanced: inlet energy inlet rate as well as energy the outlet rate. So that's why this statement: the total rate of flow of all energy streams entering the control volume must be equal to the total rate of flow of all energy streams leaving the control volume. So when I say all energy streams, I just do not mean either heat or work. I mean both. So there are two kinds of interactions happening at the boundary: the heat interaction and work interaction. So I have to take into account all those interactions taking place. So I can write the energy balance equation in this form. So m dot 1 E1 plus this d bar q by dt, this must be equal to m dot 2 E2 plus dw by dt. Now what is this term m dot 1 E1 and m dot 2 E2? What is E, small e? What is capital E? Capital E is the total energy, no? So this total energy per unit mass is nothing but specific energy. Correct? This is nothing but the specific energy or energy per unit mass. So at inlet, m1 dot is the mass flow rate which is entering at the inlet, and it is carrying some energy with itself in the control volume. So this term indicates the energy carried by that mass while flowing in the control volume. So apart from heat and work interactions, you have the energy carried by the fluid at the inlet. So I have to multiply this mass flow rate by the energy, specific energy. Now this is per unit mass. This is per unit mass. So this term indicates the energy carried by the mass flowing per unit time at the inlet. So same way, this is the energy carried by the carried away from the control volume by the mass m dot 2 at the exit. So both these terms are on rate basis. This is per unit time. This also is on per unit time basis. Is it clear? So same way, these two interactions, heat and work interactions. So this is simply your energy balance equation and nothing else. So note down this as equation 5. Now what we have to do is we have to substitute for this term from here. So this right hand side expression you can put here, and then we'll also learn how to expand this term, specific energy. So we know this capital E is made up of that EK plus EP plus U. We have seen this, right? Or if I simply write in per unit mass basis, this E can be written as per unit mass. So this will be EK plus EP. Now this is kinetic energy per unit mass, potential energy per unit mass. And if I use small u, it means internal energy per unit mass. So that way we are going to expand these two terms next. So before that, I have just substituted for this term dw by dt and rewrite the equation, the same expression as it is. So name this as equation 6. And now I am expanding that term. So combining the terms of suffix 1 and suffix 2 together. So whatever the terms which have the suffix 1, I am taking it on the left hand side, and the terms having suffix 2 on the right hand side. And this is how this equation is rearranged, right? I am expanding that term, small e. So small e is Ek plus Ep plus U. So this is per unit mass. So Ek will be replaced by C square by 2. Now what is C square by 2? See, the kinetic energy is given as half mv square U right now. So instead of V, I am using symbol C for velocity. So I will write half mc square. Right? So kinetic energy per unit mass, I have to divide this by mass. So this is how the kinetic energy per unit mass, which is Ek, will become C square by 2. And same way, we know the potential energy, we write it like mzz, right? So if you divide this by mass, so potential energy per unit mass is Ep, which will be equal to zz. So this term is replaced by zz, and this U is nothing but this specific internal energy will remain as it is. So use this substitution 8 or replace the small e here, E1 and E2 using this expression. So just add the coefficient, like if you are replacing this E1, you will write C1 square by 2 plus ZZ1 plus U1, and if you are replacing E2, you will write it like this. So use those substitutions and write the equation. Rewrite equation 7. So this is done here in equation 9. So you have this lengthy equation m1 dot into bracket c1 square by 2 plus z1 plus u1 plus m dot 1 p1 v1. This is the flow work plus d bar q by dt. This must be equal to m2 dot into the bracket. The same quantities are there, only suffix is different. And remember, this d bar q by dt is on the left hand side of the expression, and d bar wx by dt is on the right hand side of the equation. Reason being, you go back and check the steady flow device. So there you will find d bar q by dt is entering the control volume. So this is what you can say, the heat supplied per unit time to the system, and d bar wx by dt is the work extracted from your system. That's why that arrow of d bar wx by dt is outward. Go and check the diagram. It is clear there. Fine. You can simplify this equation 9 further in this form. Now what is done here is, you can combine the terms like u1 and p1 v1 together, taking m1 dot as a common from these two terms, and what remains inside the bracket is u1 plus p1 v1. And we know this is nothing but the definition of specific enthalpy. H is equal to U plus PV, right? So this must be H1 then. Similarly, on right hand side, U2 plus P2 V2 will be H2. So this is how this enthalpy is introduced here. And rewrite equation 9 in terms of specific enthalpy. So this is your final form of the equation, steady flow energy equation. So this equation is nothing but steady flow energy equation. This is on rate basis. Rate basis means all quantities expressed in this equation are per unit time basis. Means this is the heat interaction per unit time, joule per second, work interaction per unit time, joule per second, and these are again the energies per unit time. All those energies. This kinetic energy per unit time, the potential energy per unit time. This is the enthalpy. This also per unit time. All those quantities are in per unit time basis. So note down equation 10 and call this as a steady flow energy equation, SFEE. Now the same expression can be written on per unit mass basis as well. So to do that, I am introducing again the mass flow rate. So if you have a device where there is only one inlet and one exit, so in that case I can write m1 dot is equal to m2 dot is equal to simply m dot, means mass flow rate, which is nothing but the rate of change of mass with respect to time, dm by dt. Correct? So in such situation where you have only one inlet and one exit, this equation can be further simplified and written in terms of per unit mass basis rather than per unit rate basis. So you can modify this equation. So what you have to do is simply divide this expression by this mass flow rate, dm by dt, right, or m dot. So if you divide this expression, for first term it will be this m dot or m dot 1. So this term will get cancelled out. So here you have to divide by this dm by dt, which is m dot now. So when you divide it by dm by dt, it means you are writing something like this. Divide by dm by dt is, you can say dt by dm, something like this kind of term, right? It means this per unit time, this time will be when you divide this by the mass flow rate. So same way for the work also, when you divide this term by the mass flow rate, you will get the work transfer per unit mass, this term. And when you divide by m dot here, this will get cancelled. So only the bracket multiplying term you have to remove from these two terms, and instead of writing d bar q by dt, write it as d bar q by dm and d bar dt by dm. So this is equation 11. Note that equation 11 should be used only if you have one inlet and one exit. Remember this. Means mass flow rate is one and the same, entering and leaving is one and the same. Hello, is it clear?
Sir, it is used only when there is the same entry and same exit.
When you have only one inlet and one exit.
Okay.
See, you can have the situation where, let us say this is your device. So I can have only one inlet and one exit. So if this is a steady flow device, then this condition is must, mass flow rate should remain constant. So this
Yes.
inlet and outlet mass flow rate must be same, right?
Yes.
But if I modify this device to something like this, now I have added, this is one inlet, this is second inlet, this is exit, and this is also exit. So I can have m1 dot the different mass flow rate entering, m2 dot different mass flow rate entering. This can be different, and this can be also different, no? Right? Getting me or not?
Yes. Yeah.
So this should be used only when you have one inlet and one exit, otherwise not. See, the most general form of the equation which we are going to use throughout this course is equation 9. I will always try to use this equation first. Unless and until it is must to use equation 11, I am not going to use it. I will prefer using equation 10 only. Now this is all I already explained. The last paragraph I already explained. So equation 10 and 11 are known as the steady flow energy equations for a single stream of fluid entering and a single stream of fluid leaving the control volume. So we have derived it using single stream inlet and single stream outlet, right? However, you can generalize it. How to generalize we will see in the next slide. So all the terms in equation 10 represent the energy flow per unit time. So they will be measured in joule per second all the time, right? Whereas the terms in equation 11 represent the energy flow per unit mass. So those quantities will be measured in joule per kg. Remember this. Now can I go to next slide?
Yes, sir.
Okay. So still we have 10 minutes now. Maybe we'll try to cover one or two slides and then we'll stop. So we'll cover this part. So flow device with multiple inlets and outlets. Just now I was talking about this situation, correct? So what you see in the picture is there are two inlets, section 1 and section 2, and there are two outlets, section 3 and section 4. And all those interactions are noted down in the diagram. So how I write the mass balance for this? Now mass balance should be whatever the inlets are carrying the mass, the same mass must go out from the outlets. So this first equation m dot 1 plus m dot 2 is equal to m dot 3 plus m dot 4 is nothing but the mass balance equation. Is it clear? Where all these mass flow rates might be different. So the same expression can be further modified in this form. So I am just replacing that m dot by rho AC here, right? And in thermodynamics, instead of density, the specific volume is a more relevant term or more widely used term, specific volume in thermodynamics. So that's why we write it in terms of specific volume, A1 C1 by V1 and not just by rho 1 A1 C1. Whereas if I talk about fluid mechanics, I would prefer to use density instead of specific volume. Understand this difference? So this is about mass balance. Then how you will write the energy balance? So you will write it like this. See, I am just modifying equation 9 only here. Equation 9 or equation 10? I think it is equation 10 on rate basis, no? So this expression just I am modifying. How I am modifying it? So there is only one heat interaction here. So it is noted down here. One interaction, work interaction is there, which is noted down on the right hand side of steady flow energy equation. Q is on left hand side. D bar Q by dt is on left hand side, whereas this is on the right hand side. And then I am writing the energy at the inlet. So which is mass flow rate at inlet multiplied by this bracket plus mass flow rate at second inlet multiplied by this bracket. This must be equal to mass flow rate exiting from this section multiplied by the bracket plus this mass flow rate at the exit 4 multiplied by the bracket terms. So this is how I am just generalizing it. So I can have n number of inlets and n number of outlets. So I have to just keep on adding those terms here in the energy balance equation as well as mass balance equation. Is it clear?
Yes, sir.
Fine. So solve this quickly. We have 5 minutes. You should be in position to solve this, or even if you are not in position to solve it in 5 minutes, we will solve it next time. Or let us just understand what this problem is. Maybe we'll solve it next time. So in a cooling tower, air enters at a height of 1 meter above the ground level and leaves at a height of 6 meters. The inlet and outlet velocities are 20 meters per second and 30 meters per second respectively. Now this is the velocity given for the air. Then water enters at a height of 8 meter and leaves at a height of 0.8 meter. The velocity of water at entry and exit are 3 meters per second and 1 meter per second. So both velocity, inlet and outlet velocities for both the fluids are given. One fluid is water and the other is air. Then water temperature 70 degrees C at the entry and exit. Right? So what is done in cooling tower is you are cooling the water from 77 degrees C to 47 degrees C using the air which is initially at 30 degrees C. And in cooling the water, doing so, what is happening is air is getting heated from 30 degrees C to 70 degrees C. Correct? Now the cooling tower is well insulated and a fan of 2.5 kilowatt drives the air through the cooler. Find the amount of air per second required given 1 kg per second of water flow. So mass flow rate of water is given. And you have been asked to find out what is the mass flow rate of air. Now the specific values of air and water are given. For air it is 1.005 kilojoule per kg. Please note down this unit is given in kilojoule per kg, whereas here we will use the quantities in joule per kg. Remember this. So I should use 1005, not 1.005. Then for water it is 4.187 kilojoule per kgK, means 4187 joule per kgK respectively. And you have to use this expression, that find out the enthalpy H using this expression. H is equal to simply Cp into T, where T is the temperature in degrees C. So using the value of Cp and T, you can find out what is the enthalpy H, which will be in joule per kg. This is the schematic representation of your cooling tower. Now there are two streams. The air is entering at section 1. Now you can select the datum, any random datum like this, and note down what is the Z1. Similarly, the air is going out from this. So this is air exit, air inlet, air exit. So this height is Z1, this is Z2, right? Now water is entering from the top, So this is water inlet. So this height is Z3, and it is going out from this bottom. So this is Z4, right? And the quantity is like the velocity C1, C2 for air entering and leaving, C3, C4 the velocities entering and leaving for the water. These are given. Temperatures are also given. So all those temperatures are also noted down here, right? And most important, mass flow rates. They have mentioned mass flow rate of the air is 1 kg per second, right? Or sorry, water flow is 1 kg per second. So this is the mass flow rate of water, m.2, entering air and leaving air. So this is given 1 kg per second, and you have been asked to find out this mass flow rate, m.1, which is mass flow rate of air, correct? And apart from all this, you should note down these quantities. See what they have mentioned here, the cooling tower is well insulated, means there is no heat interaction. So if this is my control volume, this term d bar q by dt, this is nothing but q dot. So people are using different symbols. So come back to our symbolic representation, d bar q by dt. This must be equal to 0 because it is well insulated. There is no heat interaction. And as per our sign convention, the arrow is towards this, right? And we have used the symbol for the work interaction away from the control volume, right? So this term is nothing but d bar wx by dt, this term. So they have mentioned here. So a fan of 2.5 kilowatt drives the air through the cooler, right? So when the fan is used to drive the air through the cooler, it means you are forcing that air using the device, external device. Getting me or not? So this fan is actually consuming the energy, right? So you are not getting any work extracted from this device. Rather, you are giving some work input to this device. Getting me or not? Hello? Hello, are you getting it or not?
So can you explain the fan part?
See, in this device, you are supplying the work from outside. That's why this minus sign is there. So I'm trying to explain this d bar wx by dt. This term is negative because this is not power producing device. Actually, it is consuming energy from outside. You are forcing the air through the cooler, no? Hear me or not?
Yes, sir. Yes.
So if this would have been turbine, then this term will be positive because you are extracting work from the your fluid, right? But here it is happening in opposite sense. So that's why these words are important. Fan of 2.5 kilowatt drives the air through the cooler. Now find the amount of air per second required, means mass flow rate m.1. So very simple numerical actually. This is based on the last slide itself. So what you have done in last slide, you have written the energy balance and mass balance, right? So use these two equations and you will be in position to solve it. Is it clear?
Yes, sir.
Okay, fine. So I am just projecting the answer also here. This is the equation you will be using, and the answer is 3.16 kg per second. You can calculate on your own. Use the steady flow energy equation, and check whether you are getting this 3.16 kg per second or not. We'll discuss this in the next lecture. So I think we should stop now, right? Wait a minute, let me download Attenues first.